Хорошо, а звук там есть? Звук. Раз, раз. Есть? Хорошо. Okay, so today we're going to start, I think, the last chapter of this course, chapter 4. So I'm going to call this derived functors. But we're going to discuss some other topics in this chapter. So I'm going to start with essentially general terminology. So first section, complexes. I actually already defined complexes in abelian category. Let me just briefly review what we have. So a definition that we have many parts. So the first part, a chain complex. So usually I'm going to use notation C with a lower dot or lower bullet. So what it is just a sequence of objects. So in general, you can think about these objects in any abelian category, but for me this mostly will be R modules over some ring. So this is a sequence of objects parameterized by integer numbers, and we have maps which are going to call differentials. And the main assumption about this is that if you take two differentials, take the composition, you'll get 0. So composition of the dn, tn plus 1 is equal to 0. Yeah. Sometimes people don't want to write all these indices, so they just write d squared is equal to 0. Of course, there is a kind of dual definition to this. Co-chain complex. Well, this is essentially the same thing, but I'm using upper bullet, and the maps are now going in the other direction. So I have Cn minus 1, the differential d, the upper index n minus 1 goes to the Cn, next differential d to the n, Cn plus 1. So the difference is that the differential in the first part of the definition is decreasing the degree, and this is increasing degree. So again, the same condition, if you take composition of two differentials, you get square. So this square root is 0 as before. Well, this makes sense in any abelian category, but for me, in this last chapter, I'm mostly going to talk about R modules. Well, the main reason for this, in some steps I want to use the so-called diagram chase, and for diagram chase I need elements. So essentially, well, when we come to this, I'll explain how you can do this in any abelian category. Well, it is in the category of chain complexes, not in. Yeah, of course, from the theoretical point of view, there is no much difference, because whenever you have, say, a co-chain complex, you can form a chain complex by the following rule. So theoretically, it's really not important, but it's important in applications. So there is a standard convention for the, say, resolutions. We're going to see this in a moment. Okay, so the second part of the definition is the following. Well, I take some complex. Yeah, so I essentially am going to talk about the chain complexes, and you can do all the same things for the co-chain complexes. I just don't want to repeat everything. So you introduced the notion of the n cycles. So this is by definition the kernel of the differential, n cycles. Then you have boundaries. So b sub n of a complex. This is by definition the image of the dn plus 1, and these are n boundaries. And of course, then you can introduce the notion of a homology. So the homology for the chain complex, this is a quotient of the cycles by the boundaries. So essentially, this thing measures how far this chain complex is far from the exact complex. Recall that the exactness means that the image of the previous differential is precisely the kernel of the next differential. If you look at the definition, that means precisely that h lower n is 0. Okay. Yeah, so dual definition for cochain complex, you get the notion of the n cocycles, n coboundaries, and n cohomology. So 3. So the category of chain complexes. So the notation I'm going to use is CH. Well, I can write A, where A is some abelian category. Actual most important example will be an example of R modules. So what's this category? Well, objects of this category are just complexes. Chain complexes. And what are the maps? So the maps are, say take category, well, take two objects in this category. Let's call this C and C prime. So the maps, this is a sequence of the maps from the Cn to the Cn prime. So let's call this maps Un. These are just maps in the abelian category A. And additionally, we have condition that this kind of commutes with the differential. So d prime n Un is the same as Un minus 1 dn. So again, for shortness of the notation, I'm going to write U with a lower dot as a map from the C with a lower dot to the C prime with a lower dot. So these dots are usually indicating that I'm working with a complex, not just some object in the abelian category. Okay, part 4 of the definition. Well, I can introduce the so-called graded home. So the home with a bullet between two complexes. So this is by definition will be a product of home with the index d. So d is any integer. So the home with the index d between two complexes. Well, and what it is? Well, here in this definition, this Un, or U with the bullet, if you consider this, all this information together, this is a map of degree 0. It preserves the degree of the complexes. Potentially, you could have maps that doesn't preserve the degree. Well, an example of such map would be a differential. Here, this is decreasing degree or increasing degree. So we can consider this in general. So home with the D for two complexes. This will be all the maps. Say, again, component Un is a map from the Cn to the Cn plus d prime. And this is just a map in the underlying abelian category A. So in the case of modules, it's just a map of modules. Notice that here I don't have any conditions commuting with the differential. So it's just all the possible maps of the fixed degree. And here this is just, well, maps that can be presented as a kind of infinite vector of such maps for all degrees. And maybe I can also introduce some notation. Well, whenever I have a map phi that lives in the home D, for the shortness, I'm going to write something like this. The degree of phi is D, or the absolute value of phi is D. Just to indicate that we consider maps of the given degree. So here on this home with the bullet, I can introduce the differential. So there is a differential D. So the nth component of this differential, so large D, from the home n C C prime to the home n minus 1 c prime. Well, by definition, this differential, if you apply this to some map of degree n, well, you get the following map of degree n minus 1, which will be just a kind of graded commutator. So get d prime f minus 1 to the n f d. Well, I'm going to leave this as an exercise to check that actually d squared is equal to 0. So indeed, this is a complex. So what we've done in this part 4 of the definition, we kind of consider a new category in such a way that homes now between two complexes form another complex. And of course, the natural question is how these two categories are related, how the standard zero-degree homes that commute with the differential are related with this definition. Well, the answer is quite simple. If you take this complex home with a bullet between two complexes C and C prime, and then take Z0 here, this 0 cycles of this complex. Well, what you will get? Well, you'll get something in the degree 0, so this will be maps of degree 0, but the condition here that this is the Z0, it means that the D0 on F is equal to 0, which is exactly the condition that they have in this definition, that the map commutes with the differential. So this will be precisely homes in the category of the chain complexes. Well, we can go even further and try to understand the zeros cohomology of the same complex. Well, we need to take the previous answer, Z0, and take a quotient by the zero boundaries. Well, what it would mean precisely? Well, actually, what you'll get here are the homes in the homotopy category of the complexes. So actually, you can use this to define homes in the homotopy category. So the homes in the homotopy category, well, this will be, okay, let me continue this. So again, H0, home C, C prime, this will be Z0, home bullet C, C prime. Modular some equivalence relation, right? So here we can, well, in the concrete situation, we just talk about abelian groups. So this will be a quotient of this abelian group by some equivalence relation. What's the equivalence relation here? Well, if we have, say, F and G are two maps, they are equivalent. Well, if they're coming from the image of the differential, right? It means that I need to apply this D minus 1. So it means that the difference between F and G is the D with the index minus 1 of some S. Well, but more precisely, I can write this as the Fn minus Gn is D prime, well, H D. Well, sorry, not H, I'm now using S. Well, I need to write the indices. Well, what are the indices? Well, I think it has to be something like this. Well, anyway, so maybe you can see this on the diagram. So let's say we have complex C, we have Cn, Cn. So now I need to decrease, so n minus 1, Cn plus 1. There's another complex. Okay, so here is the difference Fn minus Gn. So the S has a degree of minus 1, so it's acting like this. So this is Sn minus 1, and this is Sn. Now here I have differential dn, and here I have differential dn plus 1 prime. So the claim is that this difference is the sum. So first thing is I take this composition. So this is dn Sn minus 1, and then I take this part, which is d prime n plus 1 precomposed with Sn. If you've seen the definition of the homotopy before for complexes, that's precisely this definition. So of course this has to be true for any n, when this makes sense, when the compositions exist. Okay, so that's the notion of the homotopy between two maps. So I'm going to leave this as an exercise, that the homotopy category of chain complexes is indeed a category. Now you need to check that, for example, everything is well defined, that if you take the composition of two maps, you replace, say, one map or the second map, or the both mapped by homotopy equivalent, you still get something that is homotopy equivalent. Okay. 5. It's a very simple thing. So on the chain complexes, we have canonical automorphism factor, which is just a shift by k. Well, this thing is doing the following. If I have a complex and I take the shift by k, so the convention is to write the shift after the complex, not before the complex, but well, if you think about this as a functor, you can naturally use this on the left. It's also, sometimes people do this. So the complex will have the following properties. So this new complex in the degree n, this will be the old complex in the degree n plus k. So that's indeed a shift by k. And for the differential, so if we take the differential, shift this by k, consider the component of degree n, well, you get minus 1 to the k d with the index n, I think. Yeah, so the difference has only been introduced some sign. Well, the sign is mostly for convention. Yeah, thanks. No, we shift everything in one direction. And for differential, also change the sign. Well, of course, for the maps, everything is quite simple. If I shift the map by k, I can look at the component A. This is u with the component n plus k. So, for example, how you can use this? Well, you can write that the home of the degree k from the C to this C prime, this is the same thing as the home of degree 0 from the C to the C prime shifted by k. Just reinterpretation of what we have before. Well, and the last part of the definition, part 6, if you have a map of the complexes, well, you can clearly see that if you apply u to the cycles, you'll get cycles, right? Because this thing commutes with the differential. And if you apply this to the boundaries, you'll get boundaries. So this is not a definition at the moment, this is just a simple observation. But if this thing preserves the cycles and the boundaries, actually this preserves homology. So there is an induced map H sub n of the U with a dot, which is a map from the nth homology of the C to the nth homology of the C prime. So there's an induced map on the homology, always. Yep, so there's a prime here and here. So, and I'm finish this list of definitions with another exercise. Well, if you have two maps, say U and V, and they are homotopy equivalent, then from this you can derive that the maps on the homology are the same. Okay. So the first proposition, which is quite easy, I'm not even going to want to prove this. If if you have the situation where T from A to B is an exact functor, then you can take a complex C, say in the chain complexes over A. Well, you apply T to this complex. This will be now a complex in the B, right? Because, well, it maps objects to the objects. If you have maps, the compositions map to composition, and zero map to the zero map. So the condition that this complex is preserved. Now here, for this complex, you take homology, and I claim that you obtain the same homology if you first take homology of the complex C. Well, maybe I don't want to use two bullets and say homology with the index n. So I can first take homology and then apply functor T. So this is for any integer n. Proof is another exercise, and it looks like if you've seen any homological algebra in any applications before, you probably know this. By the definition, exact functor maps short exact sequences to short exact sequences. We can look at the definition of the homology as a short exact sequence. So short exact sequences are preserved, and from this we can derive this result. Not very hard, so leave this as an exercise. That's important to note that the homology commute with exact functors. For example, we have the following corollaries. So I want to formulate this in a general form for any abelian category. No, haven't used any diagram chase so far. So corollary with three parts. So first part, if A is AB4, then we have the following. So first take the sum of the homology for the sum family of complexes, and this is isomorphic to the H, the homology of the sum of the complexes. Or taking direct sums commute with taking homology. And the reason for this, well, if you go back to the definition of A before, it exactly means that this functor taking the sum is an exact functor. So, of course, the dual statement is that if A is AB4 with a star, we can replace the sum by the product, and they will get the following isomorphism. So the product of the homology complexes is isomorphic to the homology of the product. And finally, the last part is that if A is AB5, then we have that the direct limits well, it's not a perfect notation, so I'm somehow supposed to have bullet here and also index I in all the formulas. Or maybe I just use upper I. So I is not the index in the complex, it's just an index for the family of complexes. And complex has its own index. Okay. Again, this is because taking the direct limit in the AB5 category is exact. So everything automatically follows on the previous proposition. Okay. So now we have the first statement where I'm going to use some diagram chase. So the lemma, the so-called snake lemma. And it says the following. Suppose we have a diagram with two rows. So the first row is the row of x's, the second row is the row of y's. And I assume that both these rows are exact. So the upper row is exact on the right, the lower row is exact on the left. And there are some maps here. Say f prime, f double prime. So with these assumptions, we can say that there is a short, an exact sequence. So then there is an exact sequence. Well, we have kernel of the f. Well, let me change this a little bit. I want to call this f, g, and h, because in my notes I have f, g, and h, and I don't want to confuse myself with the new notation. So there's kernel of f, kernel of g, kernel of h. This is mapped by some new map delta to the kernel, to the co-kernel of f. This is mapped to the co-kernel of the g, and finally co-kernel of the last map, which is h. Sorry, what? No, in general, I don't have exactness here or here, so that's what I can say with such assumptions. But it is true that if, moreover, if you have the assumption that map x prime to the x is mono, so if this map is mono, then the corresponding map on the kernels, so the kernel of f to the kernel of g, is also mono. And of course, dually, if the map from the y to the y double prime is epi, then the map from the co-kernel of g to the co-kernel of h is epi. So let me draw this diagram one more time. I have x prime, x double prime, 0, y prime, y double prime, h. Okay, so here I have the kernel of f, which is a sub-object in the x prime. Then I have the kernel of g, kernel of h. Here I have co-kernel of f, co-kernel of g, co-kernel of h. Well, might be this. Well, I think it's more or less clear that on the kernels and on the co-kernels there are maps. Right? If something is in the kernel of f, if you map it here, it will be in the kernel of g. Well, that is because this square is commutative. Now, the claim of this lemma is the following, that there is a connecting map from the kernel to the co-kernel. So this is the map that I call delta in the statement. And moreover part, if you have 0 here, you can add zeros to the final answer. So essentially, the proof is the standard technique in homological algebra, which is called the diagram chase. So let me, for example, use this to show that there is this map delta. So let me take something in the kernel of h, right? It's an element here. So I want to somehow construct a map that lives here. Well, I take an element here. Since this is epimorphism, there is a pre-image here, which is of course not unique, but at least there is a pre-image. So if I take this pre-image and then I map this pre-image to the y, well, since this square is commutative, this element pre-image is mapped to the given element. It is mapped, because this is in the kernel, mapped to the 0 by this map. So if I consider this pre-image and this map, it's still mapped to 0. Hence, for this image of the pre-image under the map G, there is another element. Well, actually, this element in the y is an element in the y prime. And now I take just the image of this element in the y prime in the co-kernel. So there are several easier things to check that, for example, this map is well defined. Well, the problem is that this pre-image is not unique, but at the end, when I consider the element here, I take a quotient by the x prime, by the image of the x prime, so that won't be a problem. So actually, delta is well defined, and then that everything is kind of exact at every term is the same argument, the diagram chase. Well, for example, you need to check the exactness at this term. Well, you take an element here, right, which is in the kernel, which is mapped which is mapped to the 0 here. So it has to be an element here, which is mapped by the map f to the 0. Well, the construction of the delta, right? Yeah. So an element in the kernel is an element in the x double prime. So this is an epimorphism, so I can pull it back here to the x. It is not unique, but it definitely exists. I look at this element under the map G. So it's mapped to some element G here. And since this square is commutative, the map from the y to the y double prime maps this element to 0. Since this map maps this to 0, actually the element that I'm getting here under the map G is an element in the y prime. And then for this element y prime, I take its image in the co-kernel. So this is the construction of delta. I think this is maybe the only non-trivial part in this whole proof. other more or less is trivial, so you need to just check exactness at every term, and this is done by the diagram chase. So I'm going to pretend that I prove this completely. Okay. In proposition, so let A, B, and C be a short exact sequence of complexes. Then there is a long exact sequence of homology. Well, here, what's the long exact sequence? Well, I take the homology at the position n of the complex A, map this to the homology for the B, homology at the position n for the C, and then there is a map to the Hn minus 1 of the homology of A. And after this, everything repeats. So potentially, if A, B, and C are unbounded complexes, this is a long exact sequence which is unbounded on the left and on the right. So let's look at the AN, BN, and CN. Now, of course, the fact that there are maps here from the Hn of A to the Hn of B and from the B to C is automatic because we know that the maps induce maps on the homology. So the non-trivial part is this connecting homomorphism delta n. So let's look this kind of one strand of this short exact sequence of complexes with the level n. So then I have canonical map to the AN modulo D of the AN plus 1, the same for the B and C. And then from this thing I consider map to the Zn minus 1 of the A, Zn minus 1 of the B, Zn minus 1 of the C. Okay, so this map is just the canonical map to the quotient. And this whole composition, well, actually, this is just the map Dn. Well, again, I'm going to leave this as a little exercise in the diagram chase that I have exactness here on the right and exactness here on the left. Now just look at this diagram, the last two rows. What is the kernel and co-kernel of this map? Remember, this whole map is just D. So, for example, if you look at the kernel, you kind of look at this thing, and you look at the things that you look at the classes which are mapped by the D to the 0. But such classes are precisely the same classes. Well, if you take just the kernel of the map of the differential modulo this image. So this is actually exactly the homology at the level n. So the kernels here are the homology. And the co-kernels, more or less again by the definition, because this is map D, so for the homology with the index n minus 1, you need to take Zn minus 1 quotient by the image of the previous map So the co-kernel is the homology with the index n minus 1. So just by looking at this diagram and applying the snake lemma, you'll get the result. So to this proposition, I want to add exercise that the construction of long exact sequence of homology is factorial. Well, more precisely, this means that if you have one short exact sequence of complexes and another short exact sequence of complexes and some maps, say F, G, and H, then you get the long exact sequence for the first short exact sequence. You'll get the long exact sequence for the second short exact sequence, and the maps, so delta n, so here I'll get hn of the f dot to be hn of the a prime. So these maps form together the so-called commutative ladder. G that's the snake lemma. We look at this part of the diagram and apply the snake lemma to this diagram. Then I'll get the exactness. Well, here this will be kernel, 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 and the kernels here are exactly hn, this, and this. This is a connecting map to the co-kernel, and the co-kernel here is hn minus 1 of the A, hn minus 1 of the B, etc. So we just kind of get this 6-term short exact sequences, and then just combine them all together and get the long exact sequence. Yeah, so here there's another exercise in the diagram chase. Well, I think this is an important exercise, important to know that everything is factorial. So essentially, factoriality in this square and this square is automatic. The non-trivial part is the factoriality here. So you need to do some diagram chase. Okay, now a remark, what to do if you don't have this diagram chase. I think important reason to do this in a concrete category with the diagram chase, well, just to show you another trick. Well, if you just do some homological algebra and don't have any preparations in terms of category theory, this is usually how you do this with diagram chase. So I just wanted to show you this kind of technique. If you want to do this in the any abelian category, then you have two ways to do this. Well, first way, of course, you can just prove, say, snake lemma, and then this proposition directly. Kind of, we've done many statements, well, for example, isomorphism theorems in the any abelian category. You can just come up with a direct proof that works in any abelian category. In some books, it's even written with all the details. Now you can say something like this. If you work, for example, with the snake lemma, we have finitely many objects, finitely many arrows. Consider the corresponding subcategory kind of by all, well, by these objects and the maps between them, the full subcategory on these finitely many objects, and then apply the Mitchell-Freitas embedding theorem. So then the Mitchell-Freitas embedding theorem tells us that you can think that the embedding is exact, so whenever you have any statement about the exact sequences, exact functors, you can work inside some category of modules for some ring R. So these are two ways to prove such abstract versions of such results. Okay, next section, resolutions. So again, I want to start with the definition, now with just two parts. So a left resolution, of some object, say M, say some module, so is a complex P with a lower bullet, such that Pi are all equal to 0 for I negative, and there is the additional map, the augmentation map, let me call this epsilon, from the P0 to the M, such that I have a short exact sequence. So say P2, P1, P0, epsilon, M. So this is a short exact sequence. So a left resolution is the complex that has only terms for positive, well, non-zero terms for positive indices, and there is an additional map. Now, equivalently, I can say that that's a complex, right? Just a complex, such that the zeros homology of this complex is this given object M. That would be the same thing to say. So equivalently, H0 of the P bullet is isomorphic to M. So P is called projective resolution if all PIs are projective objects. Well, in the category of modules, projective modules. And the second part of the definition is just the dualization of this part, of the part 1. So if you now have M object in the category, we can introduce the notion of the right resolution. It will be another complex such that you get some augmentation map. Right? So again, I with the negative indices are all 0. And there's an augmentation map and the map from the object to the complex. Well, in other words, we can say that zero's cohomology of this I with the upper bullet is exactly M. So, and as before, I is called, so that was called the left resolution. So this diagram here will be a right resolution of M. So I is called injective resolution if all the objects that I have here are injective. Well, let's look at a couple of examples, kind of so-called canonical examples. So in these examples, the category is the category of R modules over some ring R. So here, I want to construct the so-called canonical free resolution. Canonical free resolution. So I need to take a module, right? What would be the first, or actually the zeroth term of the resolution? Well, we know that here we have enough projective objects. Even though we know that if you take, for example, take M and consider this M as a set of generators of the module M. Then you take the ring and you get the canonical surjective map or canonical epimorphism. And of course this is a free module, and any free module is a projective module. And then here, well, of course in general you'll get some kernel. So let's call this K. But for this K you can repeat the procedure, right? So you take this K, you can cover this by R to the power K. Well, there is another kernel. Well, maybe let's call this first K K1, and the second kernel K2. Well, but then you can look at these two short exact sequences, and you have canonical map from this free module R to the K to this free module R to the M, just as a composition. This is a canonical epimorphism, and this is a sub-object here. Take a composition. So in this way, if you combine these things together, you'll get M, then you'll get R to the M, some R to the K1, and you just continue doing this. In principle, you'll get some infinite free resolution. What's nice about this resolution that this is canonical. You don't actually make any choices. What is not nice, well, because in practice this is a very huge resolution. You probably, if this say M is finitely generated, you probably want this to be just a free module or finite rank. You don't want this huge module. But by the way, there's a terminology. When you do this K1 is called the first syzygy of M. And K2 is the second syzygy of M, etc. Syzygy modules. Let me just write this. So K1, it has several notations. So sus 1 of the M or omega 1 of the M. This is the first syzygy of the module M. So for the canonical resolution, this is a kind of canonically defined module. But if you just take any resolution, of course syzygy is not well defined, but it actually well defined up to projective summons. So maybe we can prove this later on the seminar. So this is the first example, and from this first example you can see kind of the basic idea for the homological algebra, why we want to do this complexes and resolutions. Well, the idea is that if you take any module M, it's kind of a complicated object. It has some generators, but for these generators you have relations. So you can, in the first step, replace this M by the free module, which is on the basis. Okay, well, in general, you can just take the set of generators and get this free module, but there is a kernel which are relations among the generators. So then you choose a basis in the relations, right, and consider relations among relations. So this is the syzygies. So the syzygies are relations among relations. So potentially you have this infinite family. This never stops. But in some cases, well, the resolutions are finite. Well, if we have time today in the seminar, we're going to discuss simple examples like integers and polynomials and one variable. We're going to see that every module has a resolution with just two terms. Okay, so this is the first example, and the second example is the canonical injective resolution. And it's more or less the same idea. Well, here I was using that I can cover any module by a free module. Well, we know that if I look at the Q, which is by definition the Hom over Z of R and the Q modulo Z, this is injective cogenerator in the category of the R modules, which means that if I start with any module M, I can embed this into the some power of Q, And in this case, the power is just all the ohms from over R from the M to the Q, right? And then we just do the same thing. So this embedding has some co-kernel, embed co-kernel in another power of Q, etc. Well, continue this, and as a result, you'll get the canonical injective resolution. I'm going to write some sets S0, Q S1, Q S2, etc. As I can do here, I can just write R to the sum set, R to the sum set, etc. So these are canonical resolutions. Well, from the practical point of view, if you want to compute something with the resolution, it's not a very good idea to use them, but at least they give you some theoretical kind of examples that you always have resolutions. And yeah, and the idea that even if you don't have the category of R modules, just take abelian category. If you know that you have enough projectives, for example, you can always construct a projective resolution by exactly the same logic. Take any object, there's a canonical, well, there's a epimorphism from projective to this module, it has some kernel, a procedure for the kernel, combine these two things, short exact sequences together. So if a category has enough injectives, any object has a projective resolution. If a category has enough injectives, then any object has injective resolution. Okay. Proposition. So suppose we have the following information. So F is a map in the abelian category, say in the modules. I have a resolution, let me be more precise. So the P with the dot, this is projective complex. Meaning that in this complex, well, as before, for the negative indices, all terms are 0. For the 0 index, I have this augmentation map. And the only thing I know that all these PIs are projective objects. So I'm not claiming that this is projective resolution. So potentially this thing has some homology in other terms than 0. And the Q with a lower dot for the M, yeah, that was M prime. For the M, this is a left resolution. So here don't assume that Q is projective, just any resolution. So the only thing that's important that there are no higher homology, only zeros homology which are isomorphic to M. So then there is a unique up to homotopy lift of F to the map on such complexes or resolutions. So let's call this F with the bullet, from the P with the bullet to the Q with the bullet. Well, if I draw a diagram, it will be much easier to understand. So here I have M. For the M, I have this projective complex, so P0, P1, P2, there is M prime, there is some map F here. Here I have resolution. So this is what is given to me, right? This is, P kind of always, huh? Dun, dun, dun. Thank you. Well, I think you're right. Maybe I need to erase this 0. Okay, so the claim is that I can leave this and construct map F0, F1, F2, etc. all such maps, such that all the squares that I get here are commutative squares. This is the definition of what it means to have a lift. And this lift has to be unique up to homotopy. Okay, well, let's look, for example, for F0. Can we? Well, in all such statements, kind of the proof always by induction. You construct F0, and then you assume that you have F with the index n minus 1, construct Fn. So let's start with F0. So here, I know that P0 is projective, right? And I can look at this composition from the P0 to the M prime, and from M prime to M. So this is the map. And by the definition of P0, it has the lifting property. So the map, so this is epimorphism. Hence, any map from projective to M can be lifted here. And this is F0. So F0 we get just by using the fact that P0 is projective. So that was an easy observation. Well, let me say that P0 is projective. So this is projective. This implies that there is F0 such that the first square is commutative. Now I want to show that there are all such Fn's. So the proof is by induction. Well, I just look at the Zn of the P. This is mapped to the Zn of the Q, right? We know that any map, or this map is F with the index n. So we know that any map induces a map on the cycles. Now, using the exactness of the Q, I have the surjective map from the Q with the index n plus 1. Right, and hence, here I also have Pn with index n plus 1. There is a map here, and the same logic. Take this projective module, take this composition here, this is surjective, hence there is a lift here. Okay. So this proves the existence for any n. So now we need to show that there is a uniqueness up to homotopy. Well, let G with the bullet be another lift. Then I can look at the H with the bullet, which is just the difference of these two lifts. So what we want to show, the goal is to show that if you look at the Hn, then this is dsn plus sn minus 1 d. So we want to show that there is such a map S, that we have this formula. Well, of course, we assume that Sn is equal to 0 for n negative. So, for example, this means that the H0 is the D of the S0. Right? So the first formula in this hierarchy of formulas parameterized by positive integers is this formula. So we need to understand that such a 0 exists. No, but this I think is more or less clear because, well, this is where you work, right? So you get F0 minus G0 here, but it lifts actually the 0 map. So if this is just a 0 map, well, then say this composition is 0, hence it is actually a map. Well, actually, if this is 0, it factors through some map here. So I'm using the same diagram, I probably need to erase something. So this will be 0. So I'm looking at f0 and minus g0, which is h0, right? So this map. So then the difference here is just 0. So this square is commutative. So if I go like this, I'll get 0. But this means that actually this map is not mapped to the Q0. It is a map to the kernel of this map. And the kernel of this map, well, it's actually the I can think about this as this is exact. So the kernel of this map here is the same map, the same thing as the image of this map. So I get the map here, which is precisely S0, and this is differential D. So for the H0, we get this. Now let's show that this formula makes sense for any n, again by induction. So I can look at the Hn minus Sn minus 1d. So that is a map from the Pn to the Qn. So if I take a composition with d of this thing, now I'll get the following. Well, I get dHn minus, now on the next step, I want to use this formula, but for the index not n, but n minus 1. Well, I do this by induction, so I can assume that for the n minus 1, this formula is true. So then I'll get minus h n minus 1 minus s with the index n minus 2 differential, and then I have composition with the differential. So of course, this is well, this last term, since I have d squared here, this will be 0. So I'll get dhn minus hn minus 1 d. But this is 0 since this is a chain map. So this whole thing is just 0. So in other words, I get the following. I have Pn. Here I have a map to the Zn of Q. So the map is the same, Hn minus Sn minus 1d. So here there is Qn plus 1, so the surjective, the epimorphism here. So this I know because I just proved this. I proved that the composition with d is 0. So Pn is projective, there is a lift. So this lift is precisely Sn. Right? So I just proved this formula for the index n. Well, is it clear how I'm going to this formula to this formula? Well, here this term is automatically 0, right? It will be d squared, and I'll get dhn minus hn minus 1 d. And this is 0 because hn commutes with d. This is a chain map. So yeah, I think we've done with the proof. Well, now we can see that we have a corollary. So let P and P prime be projective resolutions. Then P and P prime are homotopy equivalent. It's a special case. Well, of course, you can see that if this P and Q that they have in the theorem are both projective resolutions, then clearly conditions are satisfied. So then by the theorem, the proof is more or less, of this corollary is more or less immediate. Just notice something like proof. You have P, M, again M, P prime, to augmentation maps. So we can take the identity on the M here, right? And just leave this identity. So let's call this map phi. And then we take identity going in the other direction, and let's call this map psi. So get maps phi and psi going in the other direction. But if you look at the composition in one order or the other order, you can notice that this composition is actually something that is lifting the identity on the M. But this lift is unique up to homotopy. So for example, the identity on the projective resolution is the lift of the identity on the M. So this has to be homotopic to the one, say, so I first apply psi, one on the P prime. And this is homotopic to the one on the P. Okay? So the resolution is unique up to isomorphism, but in the homotopy category. Yeah, I'm proving this for the projective resolutions, but of course it goes without saying that the same is true for injective resolutions, of course. And the injective resolution is also unique up to homotopy. Okay, so we've done with some preliminaries. Now let's go to the interesting stuff, the derived functors. This is probably the most important thing in the homological algebra. So what's a derived functor? Definition, again with two parts. So let's take f to be a right exact functor from some abelian category A to other abelian category B. Assume that A has enough projectives. Well, if this is a category of modules, not a problem. Then we can define the left derived functor, the left derived functor of f. This is the following thing. So notation is L with a low index I of f. So that's a new functor. And if you want to compute this on some object A, this is what you do. You take, well, you take a resolution, apply functor to this resolution, and then compute the corresponding homology. So here, P of the A is a projective resolution. Okay, questions about the definition? So if you want to compute the left-right functor of an object, you replace this object with the resolution, apply functor to the resolution, and then compute the corresponding homology. So kind of theoretical definition, but essentially what we're going to do in the rest of this course is just compute examples of such things and prove general properties of such things. So of course, as usual, if you have this version with the projective objects, you have a dual version with the injective objects. Yeah, I want to emphasize that this only makes sense if A has enough projectives, then you have projective resolutions. Without projective resolutions, well, this doesn't make any sense to use this definition. Okay, the version for the right derived functor is the following. You take now a functor which is left exact, and you assume that category A has enough injectives and the right derived functor are with the upper index I, f, if you want to compute this on the object A, then you need to do the following. You take object, replace this with the injective resolution, apply the functor f, and then compute the cohomology. So here I is injective resolution. Okay, if the first part makes sense, I hope the second part also makes sense. So, example, there is a little problem at the moment. With this definition, we don't even know that this Li or this thing is a functor. We also don't know this is additive functor. So let me check this in a minute, but I want to first state and show you two examples. And these are two most important examples to us. So the first example is the xi between, say, two modules m and n, or more generally, two objects in an abelian category. So say if this is over ring, R is also used as an index. So this is by definition, you take the right derived functor of the functor h with low m, and then compute this thing on the object n. So we know that h with a low m is the left exact functor, so this works. And the second example, 2, is the Tor with the index I. Again, I'm going to think about this as over some ring R, and I have two modules m and n. So this will be, by definition, the left derived functor Li, or the functor m tensor product with something, and then I compute this thing on the module n. So here it's important to notice that m is the left module, no, m is the right module, and n is the left module. So we have two very natural functors. Well, in any abelian category, we have this functor hom, which is when you fix the first argument m, this is h with a lower m, and over ring R, you have a tensor product, and then you can kind of ask what are, well, we know that the hom is left exact, so it satisfies this part of the second definition. Tensor product is right exact, so it makes sense to ask about the derived functors. And these are probably the two most well-known derived functors. I want to say that X makes sense in any abelian category, Tor is not. Tor is using some additional structure, the tensor product. You can say that in any abelian category you have something like tensor product. So this is a ring, and this is part of the notation for the derived functor. Well, sometimes to avoid confusion, people write something like this, but now this looks like real numbers. So probably I'm not going to do this. Well, when you type something, you use boldface for the R and L, then it looks much nicer. Okay. Now let's return to the general definition and prove proposition that kind of summarizing the proposition, summarizing the basic properties of the derived functors. So first is that L0 of f is isomorphic to f. 2, that Li of f is independent of resolution, and 3, Li f is additive functor. Yeah, so that's true. Yeah, I just wanted to say something, another comment. Well, to be completely precise, this definition doesn't make much sense, right? Because it depends on the resolution. So it's kind of correct definition would be this derived functor that also depends on the chosen resolution. So in this proposition, actually proving that it doesn't depend. And from the general kind of functorial perspective, it's not a very nice definition. Well, you need to choose a resolution, you need to check that it doesn't depend on the resolution. Well, sometimes people do the following, well, over a ring at least. You can say that you choose the canonical resolution and use this definition with the canonical resolution. And then since the answer doesn't really depend on the resolution, because, well, part 2 of the proposition, in practice we can use non-canonical resolutions. Now the proof for this statement, I would say that it's more or less trivial, all the statements here. So for one, well, since I have the right exactness, right, then if I look at the beginning of the projective resolution and right exactness give me the following. So f of p1, f not f of a. Right, so at least I get this exact sequence by the right exactness. But now, what is the, we know that the L0 of the f on A, this is homology at this term. But since this is exact, the homology at this term is precisely this thing. So this is isomorphic to the FA. And this actually explains why in the definition I want to have the right exact functor, because precisely for the right exact functors, the zeroth derived functor is the same functor. So potentially, well, you can actually remove this assumption. You can take any functor. And this still makes sense. You can still derive the functor, but the problem will be, well, that L0 is different from the functor. So 2, as was already noticed by one of the previous propositions, where we proved the uniqueness of the resolution up to homotopy. Now 3. So we want to show that this is an additive functor. Okay, so let's check that this is a functor. So suppose I have a map from the A prime to the A. I have resolutions, P prime, which is a resolution of A prime, and P is the resolution of A. Now we have, so we can choose a lift of F. So this will be a map F with a bullet from the resolution P prime to the resolution P. Now if I look at the homology, so this map on the homology actually doesn't depend on this lift, right? Because if you have two different lifts, then they are homotopy equivalent, but maps which are homotopy equivalent give me the same maps on the homology. So this map doesn't depend on F. Hence, this is indeed a functor, so we get the map on the maps, not just on the objects. Well, then of course,
Что значит значение вот последней строчки?
this one.
Вот оба. В левой части что?
Well, I have two complexes. In this case, this is just projective resolutions. Now, on these complexes, I have this map, right? Now I can take the functor f, which is given to me, and apply this f to everything in this diagram, to all the objects in this complex, to all the maps in the complex, to all the maps here. And then just look what maps I induce on the cohomology, or on the homology of the complexes. This is what I have.
Что отвечает f от f итома? Что там индексы делают?
No, just it means that just the map that you get. So if you have, say, pi here, there are some other things. You have, no, this is prime, this is pi. Now you can apply f here. So before it was a map f with the index I, right? But now, again, you're applying the functor to this thing. And this is the diagram that you get.
Тогда что это интерпретер делает в этих значениях? Это казалось бы, что это ноль, что она должна быть. Просто я не очень понимаю, что такое ошибка, потом f от интерпретера, потом вот.
Well, this is a map. Well, to a map, it makes sense to apply hi, right? That would be the thing that, well, that acts on the homology of these two complexes. Maybe I agree with you. Maybe I just remove this thing, the argument. Is this better?
А теперь это строчка из вещи в меню самому просто, я не понимаю, что сейчас происходит. Здесь это просто стрелочка ошибка f от f до базы.
Well,
Ошибка f от f, там я вообще не понимаю, что значит.
yeah, this doesn't look good. Let's check. Let's correct this. So this is the map, right? And this has to be mapped from the homology of the hi f of the p prime to the hi f applied to the p with the bullet. Is it better? Yeah. Okay, so we have a function on objects, we have function on the maps. Finally, I want to check that this is actually a functor. To do this, I need to check two properties. So I want to say that the identity on the object leads to the identity on the resolution. Hence, the derived functor on the identity is the identity. This is the first property of the functor. The second property, if I have a composition, so then composition of the lift, the composition of the maps. So these two observations together tell us that LIF is a functor. So finally, map F with the bullet plus G with the bullet lifts F plus G. So hence LIF is additive. So it maps sums to sums. This is the end of the proof. So let's take a break. Думаю, небольшой, минут на 10, не больше. Что у нас есть решение задачи, которые мы в конце прошлого семинара разбирали? Сейчас у вас обоих есть, да?
Я забыла это. Я собиралась.
Ну тогда я думаю, как бы вы все равно только один решите, поэтому вставать, наверное, не надо, просто разговаривать всю доске. Okay, so let's look at the solution of the problem from the previous seminar.
I have two steps. Just of all, first of all, I suppose that passive object of injective object is injective, then prove that sub-object of projective is projective. And I don't prove in other direction, but we can change all arrows. So now let me be projective with some sub-object. Then for two injective objects. For injective object J, I is also injective, and there we can create such arrow because if I is injective, we have such arrow, and now P is projective, so we have this arrow, and this composition will be arrow J, and have some computation. For example, if this is J, okay, this. Then we can say that I just want to prove that this composition is the same as this thing.
No, I want to say that this is more or less clear by the construction. So whenever you have a triangle, by construction it's commutative triangle, so everything is commutative.
So
Yeah, but the problem is, if you want to show this is projective,
Сначала.
First step is just the first step. If we have injective object there, then we can construct, because then I is also injective, so we can construct this arrow by definition of injective object.
Так, а G это что?
J сам injective, некоторые инъективные объекты. То есть
Ну,
я сначала
например,
проверяю.
что сверху?
Что? Сверху у нас P проективный, а Q мотивный, конечно, не проективный.
А G вообще как бы он не связан с тем, что сверху. Это
Да,
просто
не
такой.
связано просто любой инъективный. И сейчас мы докажем любого инъективного, а потом сведем любых инъективных. Значит, если if J is injective, then I is injective. Our assumption, then we can extend this arrow to, we can have this arrow, then SP is projected to have this arrow, and so we have this composition which gives us an arrow from U to J. Now for any two objects X and Y, let's do something like that. We have enough injected, so we can do something like that. There we So we have some map there because Y is a kernel of J. So we have map H. Then kernel of IJ is injective, so we can extend this map to.
I'm not sure that I understand. So the I is just the embedding into injective,
Into some
and
injective
this is just the kernel of this embedding.
of this composition.
I and J. Okay. It looks like another parenthesis for me. Yeah. Okay. Now this makes sense. Yes. Mm-hmm.
IJ. Then we have this composition, and we can before for Q, and Q is the same. We can have arrows there. Yeah. No, it's somewhere else. This is now we want to have slideshow, and how we do it. We know that some. Okay, let's do this. Again, kernel I. There we have some map. It's everything Q. This is only P. So QHF is the same as IEP. Then this map is 0. So QH is 0 just because F is apomorphism. So this map is 0, so QH is 0. So we have 0 map from Y to kernel. So we have 0 map from Q to kernel.
Well, it looks like quite complicated argument. I think what you're doing is much easier. Well, this is injective, this is quotient, this is injective. So by the previous argument, you have this map. Hence, you can construct map from the Q here,
I
right?
already see this. And
Yeah. So the only thing we want to understand is actually this map is mapped to the X, right? So you need to show that map from the Q to here, composition with this is zero. Yeah. And
what I'm trying to do is saying that this composition is zero, so this is zero, so this is zero, and this is the same what with this composition. So this is zero.
yeah, okay.
Я не успевала понять, почему вообще. Я не видела всю эту диаграмму, потому что ты перед ней стояла. Можно просто сначала, пожалуйста.
Так, можно? Я построю, ну, значит, вот эта стрелка у нас есть по предыдущему. Вот.
Так, а что И такое вообще? И это просто какой-то...
И это некоторый инъективный объект, который X можно вложить, потому что у нас равна инжектор.
Ага. А изначально у нас эти
Изначально у нас есть X и Y просто. И стрелка из Q в Y, которую мы хотим поднять до стрелки в Q. Вот. Значит, мы можем построить вот это, дальше у нас есть ядро, оно тоже инъективно. Значит, по этому делу мы можем поднять вот сюда, и осталось понять, что можно поднять вот сюда. Для этого надо понять, что вот такая композиция 0, потому что это ядро у ядра. Да, потому что это вложение. Потому что, ну как, x ядро своего ядра. Поэтому по определению ядра, ну,
да, спасибо.
да. Ну, потому что это инъективно, как бы, вложение. Вот. Ну а да, и надо проверить, что вот такая композиция 0. Для этого я проверяю, что вот такая композиция 0. Для этого я проверяю, что вот такая композиция 0. Это понятно? Вот потому что вот все коммутативно. А f у нас еще эпиморфизм, поэтому вот такая композиция. А значит, вот это 0, и значит у нас есть все-таки хорошая степень. Ну, вот, значит, вот такая композиция 0, значит, вот такая. А значит, мы можем поднять вот сюда. В ядро. В ядро.
Mhm. Okay. So before going to some resolutions, I want to discuss a couple, or maybe three problems about finitely generated, finitely presented objects. So the first problem is, I think, is quite elementary. There was a lemma that I mentioned on the previous lecture. So take a category which is locally finitely generated, and then if you have a epimorphism and you assume that y is finitely generated, then you can show that there is some object x prime inside x, such that this x prime is finitely generated, and moreover the image of this subobject is the same, so it's still y. I used this observation in one of the proofs, so let's prove this. Ну, в общем-то, да, у меня доказательство меньше одной строчки. Хотите рассказать?
Поскольку вот поэтому, since A is locally finitely generated, we know that any object, including X, is the sum of its finitely generated sub-objects. So we directly set. So then we know that я забыла, из чего это здесь следует, но вроде как мы можем представлять и автосумму.
Yeah, that was such a general statement. I think it was one of the problems on the seminar.
Ну вот. Да. То есть здесь, по крайней мере, здесь точно можно. Но это Y. And why it's finally generated, so we know that exists I naught such that y is f of x I naught.
Угу.
То есть просто есть такой индекс, что вот это.
Да?
Ну и все.
Окей. So we have this general definition of finitely generated object in any abelian category. So show that actually this coincides with the standard definition if we talk about modules. So M, which is an object in the category of modules, is finitely generated in the abstract sense if and only if it is a quotient of some finite free module.
Generated сейчас в каком смысле еще раз?
Well, as before, as for example,
Категорном смысле.
hmm?
Категорном смысле.
Yeah. So the categorical meaning is precisely the same as the naive meaning from the point of view of generators.
only one element, mi, the sum of sum greater than sum.
Ну, сейчас равно. Какой-то слон равно. Это он
Это вот
функционирует.
так, если он, конечно, порожден,
Когда кто такие сейчас, то есть сейчас вот, конечно, порожден все-таки как модуль, наверное, если у тебя уже написано вот
это какие-то элементы. То есть мы набираем все возможные модули, порожден всеми конечными наборами элементов.
А, окей.
Вот. И это направленное множество, потому что можно объединить. The sum of these modules is greater than sum of just one generated by one element, so the sum is all module. So we have I equals to m, and mi is like one.
Oh, wait. But how do you know that these MIs are finitely generated?
They're generated by.
Yeah. That would be our standard definition in the algebra, but
And so we have immortals next bit, and just goes to.
sure to the MI, yes.
And the objective just by mi, just by
Yep.
definition.
Yeah, I don't have problems with that. That's definitely true. What I'm asking, so you want to assume that M is finally generated in the categorical sense, right? Hence, if you can present this as a sum of MIs, this MIs has to be finally generated. Well,
Да, я чувствую. Да.
То есть фактически сейчас мы доказываем сверху вниз через снизу вверх.
Через снизу.
что-то такое, да.
То есть, нет, ну в такую сторону это очевидно, потому что ну, я сейчас
Мгм.
да. Так, тогда сначала, значит, если сейчас в сумме просто любых, на самом деле, у нас было.
Мгм.
Тогда у нас здесь есть порождающие образы пальцев векторов. Вот. Тогда мы знаем, что один лежит в некоторой сумме конечной. Житых. И мы знаем, что это содержится в некотором прям потому
Сейчас,
что каждый из них содержится в некотором из m и 0, потому что множество направо.
Да, я не очень понимаю эти двойные индексы, но идея, я думаю, точно правильная.
Ну, у нас так как m равно сумме этих, то значит все иксы содержатся в некоторых конечных подсуммах, так как конечные суммы.
Да.
А теперь каждая конечная подсумма лежит в некотором конкретном, потому что это направленное множество.
Окей.
Ну а тогда все эти эксциденты с m лежат в некотором m и потому что все m карты лежат в некотором m и, потому что направленное.
Угу.
Ну а они порождают m, значит m m. Почему я подумал, что тогда проблем нет? Мы же не обязаны требовать, чтобы мысли были, конечно, рождены в категориальном смысле, мы просто берем любое. подобъект и выбираем из него.
Да, это опять
Да,
правда.
мы можем выбрать из него подобъект, который равен m. И нам надо сказать, что вот это. Ну и все. Здесь есть все репетиции.
Сейчас, что-то я не понимаю.
Мы взяли вот это. Мы не знаем, что они, конечно, порождены в категорном смысле, но мы знаем, что они, конечно, порождены в обычном.
Да.
Теперь мы нашли один из них из категорного определения, который равен модулю.
Да.
Но он-то в обычном смысле, конечно, не порожден.
Да, да,
Значит,
да.
в обычном смысле.
Да,
конечно.
окей.
То есть нам все-таки.
Надо еще раз повторить.
Я все поняла, спасибо.
Okay, so now let's go to the modules of a category. So let's take F to be a module, say, right module over some abelian category A. Then this F is finally generated if and only if this is the quotient of a presentable functor.
Сейчас прошу прощения. А проблема возникла, кажется, вот я запуталась. Проблема вот в предыдущем возникла, когда мы хотели, чтобы m стала суммой конечно порожденных в смысле категорий.
Нет, там не было проблем. Я что-то просто не понял сразу, что происходит. Там ничего, никаких проблем нету. Аргумент, по-моему, прекрасно работает. Нет, ну как и раньше, найдется такой x, что f его фактор. В смысле, да. Я не знаю, было ли это очевидно сразу, с первых дней, но вообще вот эти представимые функторы в категории модулей над категорией — это прямой аналог кольца как модуля. Представимые функторы fx Это, а если у вас на самом деле вот эта категория А написана, это просто кольцо? Ну, кольцо, конечно, не является абелевой категорией, но хотя бы как аддитивная категория, то представимый функтор, разумеется, это просто кольцо, которое рассматривается как правый модуль. Поэтому представимый функтор – это такое обобщение кольца как модуля. В этом смысле здесь то, что написано, это обобщение предыдущей задачи.
Еще раз, а как мы кольцо рассматриваем как категорию?
Ну, как аддитивную категорию, там один объект. Любой элемент кольца – это отображение из этого объекта в себя. Там композиция в кольце – это композиция стрелок соответствующих. Единица кольца – это единица категории. Ну, единица этого единственного объекта. Ну, точно так же, как любая группа – это категория, или там любой моноид – это категория. Но только здесь еще можно складывать стрелки, поэтому это аддитивная категория.
Где должен быть единственный?
А x это будет вот этот ровно один единственный объект, который у вас есть. У вас есть только ровно один единственный представимый функтор. И что это за функтор? Ну, это в точности само кольцо. Ну и заметьте, да, если вы возьмете, вот, рассмотрите это кольцо, рассмотрите соответствующую категорию с одним объектом, рассмотрите функторы все из этой категории в абелевой группы. Ну, это в точности будут эти самые, скажем, если функторы контравариантные, то это в точности правые модули. Если функторы ковариантные, это в точности левые модули. Yeah, by the way, I think I need to emphasize this. When I'm writing modules as the right modules, so modules like this, these are all additive functors from the A opposite to the category of abelian groups. And the left modules over category, this is all covariant functors. And this functor is contravariant. Hx is contravariant in this problem. It's not really important for covariant functors. You still have the same result. We just use h with a low x.
То есть линия отличается
Почему? Утверждение заключается в том, что абстрактное, опять же, определение совпадает с конкретным. В принципе, как бы можно было не знать никакой абстрактной теории и сказать, что функтор конечной порожденности вот есть такой эпиморфизм. Это по аналогии вот с предыдущим. Но оно еще и совпадает с абстрактной общей терминологией. Поэтому это как бы не просто аналогия, а некоторое утверждение.
Секундочку, почему не хорошо просто дословное повторение предыдущего доказательства? Мне кажется, мы не использовали там идею, что он был левым модулем.
Проблема не в левых правых, проблема в том, что здесь категория с многими объектами. У нас модули над категорией, а не над кольцом теперь. Кстати, тот самый Митчелл, ну, которого теорема Митчелла-Фрейда, он как в старые годы, 60 какой-то 5-й, по-моему, год, написал статью, которая называлась «Кольца с несколькими объектами», «Rings with several objects». Это были аддитивные категории, и он как бы изучал модули над ними, в общем, пытался сохранить как можно больше стандартной гомологической алгебры вот как раз в такой ситуации. Это, кстати, довольно интересная статья, по-моему, до сих пор актуальная, любопытно почитать. предел, а какой предел? Ну, да, но это требует отдельного доказательства, и это даже есть в списке задач, вот сложных задач. Там, потому что там кое-что надо попроверять. Ну, там, потому что если вы посмотрите на доказательство, которое было для множеств, мы там некоторую стрелку строили, это я ее называл, совершенно не очевидно, что это как бы ну, это отображение множеств, не более того. В этом есть некоторая проблема. Вот эта задача сильно проще, чем то, что вы спрашиваете. Ну, здесь как-то надо вот определение написать, лемма-генеты применить, не более того. Абелева категория какая-нибудь. Ну, функтор аддитивный. Сумму в сумму переводит. М? Не понял. А, вот этот эпиморфизм, ну да, его можно проверять на каждом конкретном объекте, да. Да. Это мы тоже как-то доказывали, когда обсуждали пределы в категории функторов. Давайте посмотрим.
Сначала хочется проверить, что наша принцип бесконечно порожден.
Угу.
То есть он направлен на в частности,
Угу.
на самом деле это сумма
Угу.
и сумма конечная. Тогда можно выбрать просто вот эти ошибки, потому что по леме Накаяна, леме Юнеды, значит, ну, надо взять один большой h, и ты этот h, который уже все, значит, там лежит суммы в h от x лежит сумма. Значит, здесь есть единица, переходит в единицу, значит, это тождественно Значит, это изоморфизм на инпуте, потому что поле Накаямы сумма элементов, ну, то есть вот этот вот элемент внутри h x, значит, соответствует единичке, а значит, задаваемый вот ими как элементами.
Можно просто вернуться сначала, что такое ошибка?
Это некоторый подфунктор hx.
Да, мы доказываем, что он, конечно, порожден. Выбираем некоторую направленную систему подфункторов. Да, хотим доказать, что найдется такой индекс, что h большое с этим индексом совпадет просто с представимым функтором.
А нам не надо сейчас, если это налево, то нам надо доказывать, что f, конечно, порожден.
Ну, он как фактор hx, он будет, конечно, порожден.
Да.
Потому что фактор, конечно, порожден, конечно.
Это общая была теорема такая.
Поэтому достаточно сказать, что hx, конечно, порожден. Значит, hx-то здесь задают естественные вложения в hx, а x-сумма, ну, тоже задает некоторые вложения, потому что соответствует единичному элементу, а значит, ему соответствует тождественному, ну, изоморфизму в себя, по сути. Ну, тождественное соответствует изоморфизму.
Ну да, видимо, можно было сказать, что у вас там найдется какой-то индекс, так что h с этим индексом есть некоторый подфунктор с одной стороны, а с другой стороны это он должен быть по лемме Йонеды, он должен быть как бы не только вложением, но еще и эпи, значит, должен быть изоморфизмом. Да, я думаю, что это доказывает в одном направлении полностью. Да.
Все возможные вложения в наш веб. Это даже не вложения, все возможные, естественно, вложения. Направленная система, потому что содержится
Угу.
Поэтому это направленная система. Значит, если f, конечно, порожден, значит, мы можем выбрать некоторый hx, который все возможно. Значит, есть какой-то hx, который так, да, почему f на сумме? По всем это потому что, опять же, f от x сумме по всем z, все элементы fx, получается, ну, чего-то. На самом деле, сейчас. Ну, понятно, что это сумма по всем, это по всем естественным преобразованиям hx. Чего? То есть это θ при образов единиц, а образ единиц это и есть θ. hx у нас выражается по θ, hx от x выражается по θ f от x, и единичка по θ. Значит, это как минимум сумма всех вот таких θ по θ, принадлежащим f от x. А уж сумма по всем элементам равна. Поэтому f равна этой сумме.
Ну, тут, наверное, есть какая-то маленькая проблемка, что не факт, что это же множество. Да. Ну, вы можете быстро исправить, там, вам же не нужны, наверное, все иксы, вам нужны все иксы с точностью до изоморфизма.
Да.
Поэтому вы перейдете там к скелету, а скелет у нас всегда множество. Но мы предполагаем, что все наши категории как это, и существенно маленькие.
Вообще не понимаю следующего. Вещь, которая сверху написана, что f сумма по всем иксам, она равна для любого f?
Да.
Ну,
То есть они все знаковые?
Нет, и иксы, и тета взяты для f, потому что...
Там тета, я
Потому что тета — это элементы f от x.
Ну, здесь, видимо, там можно чуть улучшить, надо брать только такие иксы, на которых f от x не равно нулю, да. Там, ну, в общем, то, что здесь написано, это с точки зрения колец, это аналог того, что я сегодня писал, начало канонического резольвента. Вы берете просто модуль и берете свободный модуль, порожденный всеми элементами. Здесь вы берете функтор и берете как бы сумму представимых функторов, порожденные как бы всеми элементами этого функтора f.
Да, и проблема с тем, что это множество.
Не, я говорю, это так себе проблема, можно к скелету перейти, и проблема снимается. Вам реально не нужны все эти иксы, вам нужны как бы для каждого класса изоморфизма выбрать один. Этого будет достаточно уже. Это наше предположение общее. Это, вообще говоря, совсем не обязательно верно. Вы можете там начать с каких-то категорий, построить категории функторов между категориями, это уже не будет так. Но мы предполагаем, что, вот, например, все абелевые категории, которые я рассматриваю, это по-английски называется skeletally small или essentially small. Это означает как раз, что скелет образует множество. Я как-то, может быть, неявно это не сказал в самом начале курса, но это как бы я предполагаю от всех моих категорий, что это так.
Видите, по грандиковским вселенным, которые просто большое недостижимое множество, значит, множество.
Ну, можно так сказать, да. Только это по-русски говорят не вселенная, а как это, универсум.
Вот, это значит, по определению конечной порожденности, собственно, есть один ошибка, который добавляется на f. И вообще говоря, мы здесь брали не так вот, потому что брали образы, ну, значит, мы просто селектив.
Угу. Ну, вроде все, да. Вопросы какие-нибудь есть? Так. Maybe it's a simple problem, but still, I think it's important to notice this. Well, I was saying that this H with the upper X is an analog of the ring, if you consider the ring as the right module. Well, we can continue this analogy and prove the following, that any representable functor is actually a projective object in the category of the right modules of a category A. Ну и заметьте, кстати, в предыдущей задаче мы, по-моему, нигде абелевостью А не пользовались. Мне кажется, это результат для любой аддитивной категории А. Но для кольца он выполняется. Кольцо явно там... А кольцо, в принципе, даже не аддитивное. Аддитивное у нас может быть нулевой объект, в кольце не может быть нулевого объекта. Поэтому, в принципе, наверное, можно сказать, что это просто то, что называется Z-категория. Этого будет достаточно. Расскажите.
Кажется, просто творение. Значит, представим сюда. Эта строчка это некоторое это. То есть пришел с какого-то это, перешел это. Вот это значит, у нас здесь есть такая стрелочка, растущая. Нету. И по функциональности композиция то же самое, что.
Да. Так, действительно, это утверждение просто переформулировка лемма Накаяма. And so if you combine these observations together, or for example, you can say that if you have f a finitely presented module, then it is true that in this case, this finite presentation is such diagram. If you look at the modules, that module over a ring is finitely presented. If this is a co-kernel of some matrix. So the analog is this. No, I'm just saying. I think if you, it's in algebra sometimes it's important to work not just with finitely generated modules, but with finitely presented modules. So for finitely presented modules, you'll get this. And the analog here, if you assume that this functor, which we consider as a module over A, is finitely presented, the analogous statement will be this. Because if this is finitely presented, or at least it's finitely generated, so we can cover this by the representable, we'll get a kernel. A kernel is a functor which is again finitely generated. So it can be covered by another representable h sub h with the upper y. So this will be presentation, and in fact we can consider this as the beginning of the finite free resolution in this category. Yeah, talking about resolution, so maybe we do just a couple of very simple problems on resolutions. Maybe I can just formulate a problem and you immediately give me an answer. So what if the ring is just the integers and the module is just z modulo dz? So construct the projective resolution for this module. Oh, do you have an idea? So what's the resolution? Yeah, so the resolution is the following. Okay, so this is more or less by definition of the z modulo dz is an exact sequence. So this is projective, it's even free, and this is projective free. So that's one simple resolution. Now let's take the ring is the same and the module is z. Now construct injective resolution for this module. Кольцо просто целое число. Да. Ну, конечно, проективный элементу не интересно, потому что он сам по себе проективный и инъективный надо построить. So, any ideas what I need to use as the zero step and the first step? Купа Z, ну, это сработает, но это сложно будет. Мы как раз с вами уже и как раз инъективные всякие объекты обсуждали в Вайбелевых группах. Было это 2-3 недели назад. И в какой-то момент мы доказали, что такое утверждение, что если у нас есть область, то те самые поля частных этой области, это инъективный. Да. Но это тогда здесь очень просто построить первый шаг. Здесь просто надо написать Q. And then take the quotient. So that's an injective resolution. Okay. So let's do the last problem for today. The ring is some field. Say, let's take rational numbers. Polynomials modulo x squared. And the module is just the rational numbers. Construct projective resolution of this module. So this is just the quotient by the ideal generated by the element x, okay? Yeah, you can notice actually that the kernel as a module is just isomorphic to the Q again, right? So the first syzygy of Q is again Q, and the second syzygy of Q is Q. So you get this infinite resolution, infinite projective resolution. Okay, I think we're out of time. So, by the way, next week we have the last quiz. The derived functors and resolutions won't be on the quiz, it will be only on the chapter 4. Mm-hmm.